Today it's our great pleasure to have Niko Schonsheck from Ohio State University, who will tell us about fibration theorems, functor calculus, and chromatic connections in O-algebras.
Great, thank you. That's a kind of a mouthful. But yeah, thank you, Martin, for the invitation, and thank you everyone for being here. So yeah, just a quick outline of the talk. What I'm ultimately sort of going to get to is this more modern setting of O-algebras and spectra. But to sort of start off, I'm going to tell a more classical story, which is just completion of spaces with respect to ordinary homology, and then use that as sort of a springboard to talk about completion in this more structured setting, namely of O-algebras with respect to the analog of singular homology there, which is what we call TQ homology. And it turns out that that's actually weakly equivalent to a more familiar gadget, namely stabilization. Then I'll get into some of my work, which is some fibration theorems for completion. So in particular, trying to answer the question, when does TQ completion preserve fiber sequences? What conditions do we need on those fiber sequences to guarantee that? And then I'll get into some connections with functor calculus and looking at the Taylor tower of the identity functor. And then time permitting, I'll tell you about some recent and future work, and that's where the chromatic stuff will come in. Yeah, and please feel free to interrupt at any point. Also, I'll try to keep my eye on the chat as well. So to begin, the sort of classical story of going back to Bausfield and Kahn, completion of spaces, and by spaces I really mean pointed simplicial sets. So the basic idea here is that homotopy groups are sort of the main invariant of spaces, but I think it'd be pretty uncontroversial to say that they're difficult to compute. So maybe given a space, we want to look at a somewhat easier invariant like homology. And so if we're handed a space X, maybe we want to build sort of the part of X that homology sees. So the part of X that homology sees. And I mean, by homology, I mean singular homology with integer coefficients. Now, a good starting point here would be the Hurewicz map, which relates homotopy to homology for us. And one way to construct that is as follows. Given a simplicial set, on each set, we can form the free abelian group. And so that gives us a functor to simplicial abelian groups, which we'll call C tilde. And then we can always forget that structure. And so we have a right adjoint back down to pointed spaces. So as with any adjunction, this comes with a unit morphism. So we have a map from X to the left adjoint and then the right adjoint applied to X. And the neat thing is, if we hit this with homotopy groups, there's a natural isomorphism here to the reduced homology of X, and this is exactly the Hurewicz map. So this sort of provides a first approximation, a spaces level approximation via the homology of X. And the idea of Bausfield and Kahn is that to get a better approximation, we iterate this map. So a little bit more specifically, that's to say, we have our unit map from X to UZ tilde X. And then we could think of applying the unit again, either sort of on the outside or the inside here. And that gives us two maps up to UZ tilde of UZ tilde. And sort of keep going this way, and we get three maps up, and there are maps down as well, provided by the co-unit. And this fills out to a whole cosimplicial diagram. And that's good. We have lots of tools to deal with cosimplicial things. So then the completion is just what you get when you glue all this stuff together in some homotopy meaningful way. So we have a map from X into the homotopy limit over delta of all of that stuff. And that is the Z completion of X. Now, the kind of remarkable thing that Bausfield and Kahn show is that often this process actually recovers X up to weak equivalence, not just up to like homology equivalence. So in particular, what they show is that if a space is nilpotent, so for example, if it's simply connected or one connected, then this comparison map from X to its completion is actually a weak equivalence, which again is somewhat remarkable because object-wise, right, this construction only sees homological information, but somehow encoded in those structure maps is enough information to recover X up to weak equivalence. And a key step in their proof is to understand when completion preserves fiber sequences. So when does applying this construction preserve certain fibration sequences? So what they ultimately show is that completion preserves principal fibration sequences. And to get this statement, we can use the characterization of nilpotent spaces as having a Postnikov tower that's built from principal fibrations. Once you know sort of completion plays nicely with respect to those, we can induct up the tower and conclude that X is complete. So that's sort of the classical story of completion here. And what I'd like to do now is sort of mirror this in a more modern setting and the setting where my work takes place. So this is completion of O-algebras with respect to TQ homology, which again, we can always be thinking is stabilization. And the big idea here is that this is a totally analogous story in a different setting. And if we're not super comfortable with operads, so O is our operad, and this is really just, we can think of this as encoding a certain flavor of algebraic structure. And we're the sort of base category, we're working in a spectra. So we're considering algebras over some operad in spectra. So for example, with this machinery, we could be considering commutative ring spectra, associative ring spectra, EN, lots of different flavors can be encoded by an operad. So just the sort of a mantra, this category that we're going to be talking a lot about, algo, what this is intuitively is those spectra which have this extra algebraic structure. So spectra X with extra algebraic structure. And that algebraic structure is encoded by the operad O. For technical reasons, essentially so that algebra is pointed, we assume that O0 is a point. And just to keep things simple for today, we can assume O1 is the sphere spectrum. So I said this was supposed to be, analogous to the story we told in spaces. So let me try to highlight that. So over here we'll have instructions in O-algebras, and over here we'll have our classical story in spaces. So, right, one way to define the integer homology of a space is through that adjunction we talked about. So between simplicial sets and simplicial abelian groups. We can take it as a definition that the Z homology of a space X is given by the homotopy groups of U, Z tilde X. The analogous adjunction and construction in O-algebras is the following. So we've got algo, so we think of that like our spaces. And then we can truncate that operad. So that is, we have O1, O2, O3, and everything above level 1, we just map to a point. That gives us a new operad, which we denote by tau1 of O. And this is basically a change. It's a change of operads adjunction. So it looks exactly like a change of rings adjunction. So just like a map of rings gives us an adjunction on the corresponding category of modules. A map of operads gives us an adjunction on the corresponding category of algebras. So we'll call this Q. Q. And it's a forgetful functor going back. And the nice thing is, really, we're just landing in spectra. So we can think of this as sort of a canonical way to take an O-algebra and factor it through the stable category of spectra. And it's from this adjunction that we define TQ homology. So TQ homology of an O-algebra. I'll try to use A for algebras and X for spaces just to keep things straight. Is UQ of A. And then we can take homotopy groups and so on and so forth. Just as a bit of a sort of foreshadowing, it turns out that UQA, as we said, is weakly equivalent to stabilization, and hence they're both weakly equivalent to the first Taylor approximation of the identity evaluated on A. If you're not familiar with Goodly calculus, we'll get there. This is just sort of a precursor.
Oh, sorry, Nicholas.
Yeah.
So I should be thinking of O-alg as, like, say, in the most basic case, as just S algebras.
Yeah. You could think of O-algebras as commutative. If you're commutative S algebras. Yeah.
Oh, but they wouldn't be, or not, or even just associative ones.
Associative is also fine. Yeah.
And then this would just be like, this is just kind of like forgetting the algebra structure. Is Q is like forgetting the algebra structure?
So Q, it's not forgetting actually. What this is, if we, so this thing is T1 of O, circle over O of your operad. So if we think about a map of rings like R to F, ordinary rings in the good old-fashioned sense, then there's an adjunction between the module categories. And this is S tensor over R of blank, and this is like an extension of scalars functor going backwards.
Okay, so sorry. So mod S is just like the unit of the tensor unit, or like the sphere or whatever.
Yeah. When I write, yeah. So this is spectra.
So that's spectra, but O-alg is like ring spectra or modules over a specific ring spectra.
It could be that. In general, it's those spectra which have extra algebraic structure. So this could be comparing, like O-algebras could be commutative ring spectra, and then this functor would take you to ordinary spectra.
And in that case, topological Quillen homology does recover the usual topological Andre Quillen homology of Pastera-Mendel, right?
Yeah.
And in the case of, say, an A infinity or E1 operad, is it some kind of topological Hochschild homology or a variation thereof?
I'm not sure, to be honest.
But that would be an example that fits into the framework, right?
Yes. Yeah.
Okay.
Certainly.
Okay.
Yeah.
So
I mean, the most general.
You're looking at this just from the point of view of like operads. So this is just like O-algebras you represent as some like spectra with an operad structure.
It's not that they have an operad structure, it's their algebras over some operad in spectra. So if you take O to be the commutative operad, which is just the sphere at every level, then you get commutative ring spectra.
So their
O-algebras is commutative ring spectra.
Okay.
Yeah. Does that answer your question?
Kind of. I guess you're just thinking of this kind of in a formal way.
Yeah. This is pretty structural stuff. We don't. I haven't worked. We don't know specific. Let me rephrase that. I would like to understand, if I take O to be an EN operad, what this thing looks like, but we haven't sort of gotten there yet. We're trying to fill out the basics of how this category behaves and some natural invariance on it.
Okay. Thanks.
Yeah, thanks for asking. And so let me just say there's several names that should be mentioned here. As Martin pointed out, Maria Bastera originally came up with this idea of topological algebraic Quillen homology. And Mike Mendel also works on it, Nick Kuhn and Harper House. Okay, so that's sort of, the big picture. We're thinking sort of O-algebras is kind of analogous to spaces. Spectra is sort of like our spatial abelian groups, and then we have this construction of homology. So in the same way that we constructed the Z completion of the space, we can construct the TQ completion of an O-algebra. So given an O-algebra A, its TQ completion is precisely the homotopy limit over delta, same kind of resolution. So we've got UQA, UQ squared, and so on. And again, just, yeah.
Greg, I just wanted to continue with that question just because I don't quite understand. There's something I'm wondering about. So
Sure.
O-algebra is like a spectra with extra structure.
Yes.
But Q is not the forgetful functor.
Correct.
Okay. Okay. Or not necessarily. It could be, but yeah.
Yeah.
It's the indecomposables.
It's the
it's more like
if sorry, that probably would have, if X is a commutative ring spectrum, and if O-algebras is modeling commutative ring spectra, then TQ of X morally looks like X mod X squared. So you're sort of killing off higher algebraic structure.
Oh, okay, thanks.
Yeah, thank you, Martin. Cool, yeah, so we have this completion construction here, and we have a natural map from A into the completion. And just like in spaces, we can ask when can we recover an O-algebra just from its TQ homology in this way? And what Ching and Harper show is that if an O-algebra is zero connected, then that comparison map is a weak equivalence. And this should be thought of as analogous to a special case of Bausfield and Kahn's result, which is that simply connected spaces are Z complete. But Bausfield and Kahn actually do better than this, right? They show that it's enough for the space to be nilpotent. So this led me to ask, can this condition of zero connected be relaxed at all? Are there O-algebras which are not zero connected, but which are TQ complete, for example? And remember, a key step in Bausfield-Kahn's proof was understanding how completion played with fibration sequences. So I started this project wondering, if an O-algebra has a principal Postnikov tower, is it TQ complete? But at the time, there was no fibration lemma analogous to that key step in Bausfield-Kahn's proof. So that original question is still open, but what I'd like to tell you about now is sort of a step in that direction, which is understanding how TQ completion plays with fibration sequences.
Niko, so I'm following the grading convention here, zero connected, if I think of A as a commutative ring spectra or EN ring spectra, we're really talking about pi zero of that ring spectrum being trivial?
Yes, exactly.
Oh, that sounds very restrictive. Most ring spectra that I know and love have a non-trivial pi zero. So what would be some examples that do have a trivial pi zero?
Various suspension spectra probably would.
Okay, but those give you co-algebras, right?
You mean that other than it's not the unit in degree zero? So these are like non-unital things,
right? Non-unital, right? In this case, right?
Yeah. Certainly, if you do like any chromatic localization, you're definitely not zero connected.
Okay, so there are some interesting non-unital ring spectra that would at least satisfy those assumptions. Okay, but I would like, so I'm glad that you're working on generalizing that because it does sound very restrictive.
Yeah, the zero connected, to get any argument to work with Blaker's-Massey theorems, you need like any kind of cubical, somehow connectivity has to be in there. But yeah, we'll see more of that in a minute.
Sorry, if I could just say something about that. So if you have
Sure.
like something that's augmented, I guess you maybe could take the fiber and get something that's zero connected.
Yeah, that'd be a way to do it, sure. Or any, I mean, if you've got any ring spectrum, you could take its zero connected cover, just in the category of spectra. Okay, so yeah, let's talk about fibration theorems. So the theorem is this. If we're given a fibration sequence, F E of B in algeo, if we assume that the total and base O-algebras are zero connected, then TQ completion preserves this fiber sequence. And to sort of get at something, Martin, you raised, the proof essentially boils down to showing that the map from F to its completion is a weak equivalence. But in this case, F is only necessarily -1 connected. So this gives a new class of TQ complete O-algebras. So there are some interesting examples of not zero connected O-algebras that are TQ complete. So I'd like to give you sort of a sketch of the proof. I'm wondering about time and how detailed I should get here. But let me at least give you sort of the flavor of what we do.
Sorry, can I ask just one other question? When you take a fibration sequence in alg-O, does it commute with the forgetful functor to spectra?
Yeah, so the model structure on O-algebras is induced by the forgetful. So a map in O-algebras is a weak equivalence or fibration if it's a weak equivalence or fibration in the underlying category.
Okay.
But then co-fibrations are very different.
Thanks.
Yeah. Thanks for asking. So let me just sort of sketch the proof here. So we can start with this, start with our given fiber sequence, and what we want to consider are the natural maps into the various completions. Now we assumed E and B were zero connected, so we know from Ching-Harper's result that these vertical maps here are weak equivalences. What we don't know about is this one, because we don't know if that bottom row is a fiber sequence. And so the strategy is to just show directly that it is a weak equivalence. So how can we go about doing that? Well, this diagram here comes from that whole, there's these co-simplisha resolutions. So it's probably a good idea to start looking at those. So we've got F to E to B, and then to build this up here, right, we resolved each of those with respect to TQ homology. So we can take EQB, EQ squared, and so on. Resolve E in the same way, and same goes for F. Some more. Okay. So first column, life is good. This is a fiber sequence. We know that because we assumed that. But right away, things kind of go off the rails. To get this next row, we just forget about the U's for a minute. What we've done is hit a fiber sequence with homology, and generally those don't play well. And another way to think about it is, well, we took a fiber sequence, which is a limit diagram, and hit it with a left adjoint, and those also don't play well. So there's really no reason to suspect that this next column is also a fibration sequence, and things just get worse from there. So the issue we're running into is, we sort of lost control of the diagram right away. And so to rectify that, we're going to sort of fix the top row. So rather than having UQ and UQ squared F here, let's just take whatever the homotopy fiber of this map happens to be. So rather than have that UQF there, let's just stick in F0 so that this becomes a fibration sequence. And same thing here and on down the line. So this gets us a map from F into a new cosimplicial thing, which we can call F tilde. And just by commuting homotopy fibers, or homotopy limits rather, we do know that F is weakly equivalent to the holim of F tilde. Basically, just because holim of Ho5 is Ho5 of holim. So we have control of the diagram. The issue is that has sort of come at the price of having the completion of F in the picture. Right? We sort of crossed out the exact thing we were trying to analyze in the first place. So somehow we've got to get the completion of F back into the picture. And the strategy is to just take this top row and resolve each of these with respect to TQ homology. So we take that top row and it becomes the bottom row in a new diagram. So we've got F into F0, F1, and then what we're ultimately interested in is the TQ resolution of F. So we'll stick that there, and then we can resolve each of these other guys. This is the point where if this was a real chalk talk, I'd be sweating profusely from drawing all these diagrams. But the iPad makes it simpler. Cool. So we've got, even bigger diagram, and this part here is a bi-cosimplicial diagram, if you want, delta by delta shaped diagram. Now the map that we ultimately care about here is this map from F to its completion. And the strategy is, in order to analyze that map, we're going to instead analyze these other maps. So this collection of horizontal maps, sharp, and collection of vertical maps we call star. So the basic strategy is to show that the collection star and sharp induce weak equivalences on holim delta, and it follows that smiley face does too. I think for time reasons, I'll just give a very brief sketch of how each of those arguments work, so I can get to some of my other work. But if anyone has questions, I'm more than happy to chat about that at the end, for instance. So the star maps are relatively formal, actually. Essentially, one can find an extra codegeneracy in each of those diagrams, and just like an extra degeneracy of a simplicial diagram induces weak equivalence on realizations, an extra codegeneracy induces a weak equivalence on Tot, which is our model for Holen. The real work comes in the sharp maps. And the big idea is to use cubical diagrams in order to analyze what happens essentially when we take this bottom row and apply TQ homology. So just as sort of a quick example, what we ultimately show is that the map from UQF into, as we take truncated Holens of that resolution, that this, the connectivity of this map is increasing as I go higher and higher in co-simplicial degree. The way we do that is the following. Connectivity of the map from F into Holem, say delta less than or equal to 1. Oh, and I should say, sorry. Yeah, so this gets us this row, and then it's a similar argument for all of the others. So I just want to sketch here sort of how we get these bottom rows, and the other rows are similar. So the connectivity of F to this guy, we know is 2, basically from the assumption of connectivity on E and B. But the connectivity of that map is exactly the Cartesianness of the square that we get by looking at just the 0 and 1 place in those co-simplicial diagrams. So we have a Cartesian estimate on this thing, and what we want to get is a Cartesian estimate on the second row. The issue is that we're applying Q to something, and Q as a left adjoint doesn't play well with Cartesianness. But by using Blaker's Massey theorems, which just relate Cartesianness and co-Cartesianness, Blaker's Massey theorems tells us that this diagram is 3 co-Cartesian. So we take the Cartesian, turn it into co-Cartesian, and Q does play well with co-Cartesian estimates. So if we apply Q to this thing, it's still 3 co-Cartesian. Now we're in spectra though, we're in a stable category. So that co-Cartesian estimate we can turn back into a Cartesian estimate, no problem. That implies 2 Cartesian. And then the forgetful functor plays nicely with Cartesianness. So this square here is again 2 Cartesian. And then last step is to turn that Cartesian estimate into a statement about connectivity. And it tells us that the map from UQF into UQF tilde is 2 connected. So let me see if I can get, I can't get both of these on here. But so this map we got is 2 connected. That's exactly the beginning level of the second row. It works for higher dimensions, and then it works for the rows above. But this is the heart of the argument, is to take a connectivity statement, turn it into a statement about Cartesianness, take that, turn it into a co-Cartesian estimate, so that I apply Q, get a Cartesian estimate, and come back. And that's where the connectivity is used. The strategy also generalizes to pullback squares. So if we have a pullback square where well, let me just write it down. So generalization pulled x. So if we have a pulled x square, say a to b, x to y, homotopy pullback in algebra, if b, x, and y are zero connected, then the square is a pullback after TQ completion as well. Similar kind of argument works for that.
Niko?
Yeah.
For the argument in higher degrees, you need some connectivity estimates for higher dimensional cubical diagrams, right?
Yep, and all the subcubes therein.
Right, right. So what's a good reference for Blaker's Massey-style theorems in O-algebras?
Thanks for asking. Yeah, so for O-algebras, Ching Harper have a paper called, I think it's called like Higher Blaker's Massey Theorems in Structured Ring Spectra.
Oh, well, how convenient.
Yeah, yeah. It's very
perfect. Good to know. Thanks.
Yeah. Yeah, it's a very cool paper. But yeah, because you need, but once you start doing higher dimensions, you need to also look at all the different subcubes and combinations of subcubes. But it's just sort of a combinatorial problem at that point. Cool. So that's sort of the story about completion, and that was sort of my first research project. But my current direction of research is really in functor calculus and some other sort of related areas. So I'd like to tell you a bit about that. And it turns out, at least in the context of O-algebras, there's a very nice TQ homology sort of naturally comes into the picture when you talk about functor calculus. One way to understand that is TQ is the same as stabilization, and the whole point of, well, one of the points of functor calculus is to sort of interpolate between stable and unstable homotopy theory. So just for a brief background in functor calculus, this story works for both spaces and O-algebras. This is due to Goodwillie in the context of spaces, and Kuhn and Pereira work out similar sort of theorems in the context of O-algebras, as well as Harper has. So the basic idea is that just like in classical calculus, we can approximate a lot of nice functions by simpler Taylor polynomials. We can approximate sufficiently nice homotopy functors by simpler ones, which we think of as nth Taylor approximations. And this works for any homotopy functor, but when you're working in an unstable setting like spaces or O-algebras, the identity functor is actually very interesting to look at, the Taylor tower of the identity functor. So this machinery constructs anexcisive approximations of the identity functor, which we call Pn of the identity, and they arrange in a tower. So we've got identity into P1, P2, P3, and so on. And structure maps up. And as I mentioned earlier, so P1 of the identity, it turns out, is always going to give you stabilization. And one of the main theorems of Goodwillie is that if a space or algebra is sufficiently connected, and we think of this as sort of a radius of convergence, then this tower recovers X. So in the case of spaces, that first term there is stable homotopy, and it's converging to unstable homotopy. So this is a very useful construction. It's used by like Mark Behrens, for instance, to do lots of cool calculations. And a question I'm interested in is, can we say anything useful outside of this radius of convergence? So what can we say? about P infinity of the identity when A is not in a radius of convergence. Now, at first glance, this might be a wild goose chase, but fortunately, the question was answered in the context of spaces, and it's very cool. It's a really cool proof. I'm a big fan of it. So again, let me try to draw this analogy here between spaces and O-algebras. So in the context of spaces, the radius of convergence is sort of one connected. So Goodwillie shows that if a space is one connected, then this tower recovers the space. And again, the sort of analog in O-algebras, due to Kuhn and Harper-Hess, is zero connected. So if A is zero connected, then we have a weak equivalence to Taylor tower. And again, we're thinking of these as sort of the radius of convergence. Are others seeing that?
Yes, I was hearing the static.
Sorry about that.
Oh, no problem. It's gone now, right, for everyone? Okay, cool. Yeah, so what, can we say anything useful if the space is not one connected, for instance? And Aron and Kankan-Rita show that we can. So they get a result for any zero connected space, so any path connected space. And what they show is that in general, what the Taylor tower is converging to is X is the completion of X with respect to stabilization. So then one way to interpret Goodwillie's result is that, well, if a space is one connected, then it's actually weakly equivalent to its completion. So this is what the Taylor tower is sort of always converging to, and then in the special case we get X back. And another question mark is there some analog in O-algebras? So I was able to obtain not an exact analog, but the following. So this says if A is -1 connected, but its TQ homology or stabilization is 0 connected, then the Taylor tower of the identity is converging to the TQ completion of A. Now, it's a reasonable question to ask, well, does TQ being 0 connected just imply that A is 0 connected? And the answer seems to be no, fortunately, because we're also able to establish a sufficient condition. Let's call this star, so sufficient condition for star, is that if we look at the operad structure maps, so for some k greater than or equal to 2, we have these structure maps given by the algebra structure on X. If for some k, if we hit this with pi 0 and get a surjection, then TQ is 0 connected. And this essentially follows from analyzing a certain bar construction and its spectral sequence that calculates TQ for us. Now, I'd be very interested in, yeah.
Niko, is there any chance that we can drop the assumption about the stabilization of A being 0 connected, or would that be too optimistic? Or do we even know if that's false? Or
yeah, I sure would like to, but we
So as far as you know, there is no known counterexample. We might still dream that we can drop that assumption.
Yes, yeah, we could, absolutely, okay. And certainly, this really suggests that we should. The issue that we often run into when dealing with sort of going from 0 to -1 is that if you take a zero connected space and start smashing it with itself, you increase connectivity. Connectivity of smash is like connectivity of this plus one, so it goes up. When you smash -1 connected things, they stay -1 connected. So all of Goodwilli's constructions that sort of rely on, well, eventually the connectivity is high enough. If you start plugging in -1 connected things, none of that sort of works.
I see. That's the main technical problem.
Yeah. So I certainly think it could be true. I think probably the proof is going to have to be something different that's not sort of in the style of Goodwilli calculus.
Thanks.
Yeah, yeah. Thanks for asking. Okay, cool. So I think for time reasons, again, I'll sort of skip the proof, but happy to talk about it after if folks would like, and finish telling you about some recent joint work. Oop, should have a pen there. Recent work. And this is joint with Crichton Ogle, who is also at OSU. So this essentially, we're trying to study the interaction of chromatic localization and the Taylor tower of the identity, inspired by some results of Nick Kuhn, just that for some reason, Goodwilli calculus interacts really nicely with chromatic homotopy theory. So for instance, he has shown that the Taylor tower of any functor from spectra to spectra splits after you localize with respect to like En or Morava K theory, which is pretty remarkable. So that was sort of one of the inspirations to start looking at this. So to sort of set this up, again, let me, given an O-algebra A, underlying that is some spectrum, and we can consider the localization of that spectrum with respect to the Johnson-Wilson spectrum or Morava E theory. So we can consider LE of A just as an underlying spectrum. And the question we wanted to ask is, can that localization, first of all, be given a natural O-algebra structure? So could we consider this as an O-algebra? And then is there any nice interplay between this kind of localization and the Taylor tower of the identity functor? Interaction with Taylor tower. And the theorem is the following. So that there is a model of the localization which has a natural O-algebra structure. And in particular, it's compatible with the localization map is a map of O-algebras. It's not that we've given the localization some trivial algebra structure. So with a natural O-algebra structure. And furthermore, if we look at the nth Taylor approximation of that gadget as an O-algebra, that's weakly equivalent to first taking Taylor approximation and then localizing. So chromatic localization commutes with Taylor tower of the identity functor.
Niko, in the assumption of that theorem, must E be specifically something like Morava theory, a Lubin-Tate spectrum, or is it more general than that? Is it for some nice enough ring spectrum?
Yeah, the key property that we use about E theory is that it's a smashing localization.
Huh, so if you have a suitable ring spectrum E such that its Bausfield localization is smashing, that should still work, right?
I believe that. We didn't write it up that way. We're primarily interested with En, but that's really the only property we use.
Okay, so there's a good chance that it might generalize to that setup.
Yeah, and certainly, connectivity is out the window once you and localized. So we're not using any kind of connectivity or anything. So
Got it.
yeah.
Thanks.
Yeah. Thanks for asking. My notes. Yeah. So let me just sort of again give you a brief sketch of how this will go, and that should wrap things up nicely. So there's sort of three key steps in the proof. So first, we want to consider we can look at the Taylor tower of the identity. And the first step is to get sort of a nicer model for this. So the general construction of Pn of the identity is pretty big, and it in particular involves homotopy limits and colimits. So if you want to hit that with sort of a left or right adjoint, things probably aren't going to work out. And it turns out there's a very nice model for this, which comes from that same kind of change of operands adjunction. So we had that tau 1 of O. We could also just truncate above level 2, above level 3, and so on. And this gives a new pattern that's weakly equivalent, but constructed differently. This is sort of step number 1. This is originally due to Pereira in his thesis, and then Q and Pereira give a similar kind of argument. The thesis hasn't been published yet. It's a little unclear if they're using any kind of connectivity assumptions. So we do give a different proof. It was outlined to us by Nick Kuhn, which was great. He sent us an email and was like, "Hey, I think this would work," and very nice of him. So that's sort of step number 1, is to get this a nicer model for the Taylor tower of the identity. Step number 2 is to get a nice model for the E-local sphere spectrum. So obtain a nice model to call SE for the E-local sphere. And since it's a smashing localization, what this tells us is that the E-localization can be modeled as SE smash A. And it's this that one.
Nicholas, when you
Yeah.
mean, what do you mean, like take T2O tensor, circle that, and then you take the adjoint back into?
Yeah, you forget back to O-algebras.
Yeah, okay, you come back to it. So you just didn't, you left that out of the notation.
Yeah, sorry. Yeah, see, we could stick a U there. Yeah, thanks. So in particular, SE is a strictly commutative ring spectrum, and using that, that's how we get that this has a natural structure of an O-algebra. So that's sort of part 1 of the theorem. And then lastly is to get this commutivity. So big sequence of weak equivalences coming up, and I'll try to sort of highlight what happens in each of these. So on the one hand, we start with the E-localization of the Goodwillie approximation of A. Well, thanks to smashing, we have that SE smash, or that this is given by just smashing. Now, usually, as I mentioned, PN involves limits and colimits, and so it's not going to play nicely with smash products, probably. And that's where this nice model comes in. This is weakly equivalent to SE smash tau NO circle of A. And this is calculated by a bar construction. So in other words, it's the realization of a simplicial gadget. So that's at least morally, more likely to play well with smash products. So in particular, we get a weak equivalence to SE smash certain bar construction. Now, the smash will definitely move inside the realization, and then it takes some work to actually move it sort of inside the bar construction itself. But we are able to do that. And then we sort of go back. So this is the same as T analytical over O of this guy, which again is our T identity of this guy with this, with this being weakly equivalent to the E localization of A. So it looks like we're about out of time. So thank you very much for your attention.
Thank you for the very nice talk. Let's unmute ourselves and thank Niko. Are there any questions? I did have a question, if I may. I've asked a few, but
Okay.
right. So you mentioned that this research program is about O-algebras, but what happens if you specialize to certain O, like En, E infinity, so E1, something like that? Do you expect some stronger results, maybe, or do you know if there's some work being done in that direction, just trying to get stronger results about less general operas?
Yeah, I would love to get into that. So I can't tell you now, but I think that's a very interesting question. This did all start well. So this tower here, this guy started with Nick Kuhn, I think, actually, and his paper localization of Andrei Quillen Goodwillie towers, where he's just doing this all in commutative ring spectra. So he's got an analogous construction of all of this for commutative ring spectra. And then I think just historically, John sort of generalized that to O-algebras. But yeah, there's sort of a big gap there between commutative ring spectra and general O-algebras. And there's a lot of stuff in between that I think would be, yeah, very interesting to study, like En, or even like a Lie operad, structure. And then that plays into the whole bar cobar duality, Lie operad being the Koszul dual of the commutative operad. And yeah, I think there's a lot to explore there.
Okay.
Yeah.
Nice. Other questions or comments for Niko? If not, let's thank our speaker again. And thank you all for attending.
Thanks again for having me.
All right, take care, everyone.